Alice, Bob, and Eve explain Majorana particles.
Look at these magnets here. It's strange how they can both attract and repel each other depending on which end you use.
That reminds me of something fascinating in quantum computing. Majorana particles.
Oh, Majorana particles. They're quite the exotic quantum objects.
What makes them so special?
Well, normal particles have antiparticles that are distinct from themselves, like electrons have positrons. But Majorana particles are their own antiparticles.
Think of it this way. Most particles are like having both a north and south magnetic pole as separate entities. Majoranas are like if north and south poles could exist as independent objects.
That seems impossible.
In our everyday world, it is. But in quantum systems, particularly in certain superconducting materials, we can create quasi-particles that behave like Majoranas.
Imagine if I could somehow separate this magnet so the north pole is on one end of the room and the south pole on the other.
And these are useful for quantum computing?
Incredibly useful. They're predicted to be naturally protected against decoherence, one of the biggest challenges in quantum computing.
Normal qubits are fragile. Environmental noise easily disturbs them, like how a carefully arranged stack of blocks can be knocked over by a slight bump.
But Majorana-based qubits would store information non-locally, spread out across space. It's like having your information not in any single block, but in the relationship between blocks positioned far apart.
So even if someone disturbs one part of the system,
the information remains intact. For an error to occur, you'd need to disturb both ends simultaneously, which is much less likely. It's called topological protection. Think of braiding a friendship bracelet. Once it's braided, the pattern is stable. You can pull and stretch it without changing the fundamental braid.
And quantum computations would work like what?
Like creating specific braiding patterns with these particles. The patterns themselves would carry and process the quantum information.
The challenge is that we're still working to conclusively prove we've created true Majorana particles in the lab. There have been exciting developments, but it's still an active research area.
So somewhere between theory and reality, there exist particles that are their own opposites. And they might be the key to stable quantum computers. The quantum world really does defy our everyday intuition.